guys, Mr. Klein here with our third and final lesson of our chapter on Newton's laws of motion. Third lesson in the chapter, Newton's third law. That's what we're going to be talking about. We'll be talking about action-reaction pairs as well as momentum. So let's go ahead and let's get started. Now, you see this rocket actually taking off, going up into the air, and once it gets there, goes back down. Why is that? Well, it's mainly because of Newton's third law and how it acts, how motion acts on different objects and stuff, and the amount and the direction of it and stuff like that. So let's go ahead and let's go into this right here. Newton's third law of motion concerns how forces act in an object. According to Newton's third law, all forces act in pairs. In other words, every time there is one force, there's actually a second one happening. And not only that, these two forces have the same amount. In other words, their forces are equal, but they're in opposite directions of each other. If one's going up, the other one's going down. Okay, so Newton's third law of motion is as follows, and it's one that we all know. For every action, there is an equal but opposite reaction. Okay, so that's Newton's third law. The first one concerned inertia. The second one concerned what exactly is a force. And this one talks about forces and how they work in pairs in equal but opposite directions. It's important to know that the actions do not, you might be thinking, Mr. Klein, if they're equal and opposite, well, doesn't it mean they cancel each other out? No, it's because they don't operate on the same object. They operate on two different objects. As a result, they're not canceling each other out, and the net force doesn't equal to zero. Now, if you remember from the last lesson, net force is the total amount of forces acting on objects. Okay, so for Newton's third law, you have to remember that all of these action-reaction pairs that we see operate on different objects. And like I said, because the net force is not equal to zero, the object moves. So let's go ahead and let's fill out our graphic organizer. To space you out for your graphic organizer, put it in half with a dotted line. We're going to fill in top of it about Newton's third law. The bottom half is going to be about momentum. So go ahead and put this, Newton's third law of motion, and shade in purple this box. For every action, there is an equal but opposite reaction. Okay, so let's look at some examples of Newton's third law of motion. There's plenty of examples in everyday life where we see action and reaction pairs. First off, you and your friend are on your skates and you push each other. You will both go in different directions, the opposite direction of each other, rather. You know, if you're both on skates and you both push on each other, you actually go further away from each other. And if we look at this example of a skateboarder, okay, the skateboarder pushes their feet on the ground away from them, but the skateboard and the rider itself goes in the opposite direction. Okay, so the skateboard has the action of going forward, and the opposite reaction is that of the foot propelling it backwards. Okay, the next example we want to talk about is when you shoot fireworks or missiles or bullets or anything flying through the air. For example, the rocket might fly upward, but the exhaust of the engine goes downward. So if we have this example of this gun-launched missile, okay, the missile is flying to the left of your screen, but the exhaust of the missile is actually flying to the right, okay, as it goes through. There you go, okay. Missile goes to the left. The exhaust or the propellant of it is heading off to the right. Now, the action-reaction pair, remember, they're acting on two different objects. The force of the propellant acts on the missile, that's why it's flying to the left, but the exhaust itself is actually acting on the air around it. It's pushing on the air away from it. As a result, the forces don't cancel each other out, and that allows for it to move. Okay, and finally, if you paddle with a canoe, if you think about you're paddling with a canoe or kayak or something like that, you go forward by pushing the paddle in the water backwards. As we see Mythbusters, okay, with their duct tape canoe, they paddle backwards with the paddle. The paddle pushes the water backwards, and the canoe itself moves forward, okay? So the action acts on the canoe, okay, of moving forward, and it's the paddling itself is pushing on the water. So let's go ahead and let's fill out our graphic organizer for this top half, okay? There's three things to know about these action-reaction pairs. All motion consists of a pair, at least a pair of forces, okay? You have a pair of forces. They act on different objects, and the amount of force acting on these different objects is the same. They're equal in strength. So all of these connect to each other, and they all connect to Newton's third law. So that's Newton's third law in a nutshell. And let's talk about a related concept, momentum. When objects are moving, they're hard to stop due to inertia, if you remember from Newton's first law. But why do they have so much inertia? If you remember, inertia is essentially dependent on the amount of mass, and I'm going to talk a little bit more about that in a second. We can measure how hard it is for an object to stop. In other words, kind of like how much force it's moving with, how much force is needed for it to stop. Through, it seems similar, it's a concept that we call momentum that we can measure. Momentum is simply the property of an object in motion that makes it hard to stop. Okay, so this ball that's spinning on the person's finger will not stop spinning until you have an opposite force acting on it, okay? You have an unbalanced force acting on it. But the reason why it keeps on spinning is because of momentum, okay? And we can figure out momentum through a mathematical formula, which we're going to go through in the next part. Now, I know what you're thinking. You have a confusion alert. Whoa, Mr. Klein. Okay, inertia and momentum, those two things kind of sound like the same thing. Well, let's go ahead and let's clarify this. Inertia is a property of all matter, okay? Whether it's in motion, at rest, whatnot, all matter has inertia. Inertia is actually just mass. How much inertia an object has, it's the amount of mass, like I talked about in the first lesson. Momentum is something different. Momentum measures how hard it is to stop an object, okay? It talks about the force needed to apply to it over time in order to stop it, okay? So the momentum is actually just a measurement, and we only measure momentum when an object is in motion, okay? Momentum, motion, momentum, motion, momentum, motion. Okay, you got it? Good. So that means that this confusion alert, okay? I know you guys were confused. Remember, inertia has to do with mass. Momentum has to do with objects that are in motion. So let's go ahead and let's pop this into our graphic organizer. That momentum is a measurement of how hard it is for an object to stop. Kind of like velocity, acceleration, and things like that. It's different than just like a measurement like inertia. Now, how do you calculate momentum? Well, you can calculate it using this formula, P equals mv, or momentum equals mass times velocity. Now, you might be thinking to yourself, Mr. Klein, momentum sounds a whole lot like force. P equals mv sounds an awful lot like F equals ma. Well, the relationship is pretty much the same. Momentum is different than force, because remember, force involves the combination of mass and acceleration. If you remember acceleration, it's any change in velocity. Momentum involves a combination of force and velocity, or the speed and direction. If you remember, velocity is speed plus direction. As a result, here's the difference between force and momentum. For instance, if we have an object moving at constant velocity, okay, if it's moving at 10 meters per second, okay, but if it isn't speeding up or slowing down, it has no force because it isn't accelerating. It's going at 10 meters per second. However, it has momentum because it has mass and it has velocity. Now let's do a math problem in order to figure this out. So Drake has a medicine ball. That's those big, heavy exercise balls. It has a mass of 10 kilograms. He throws it up in the air, okay, and it's going at a velocity of 6 meters per second upward. What is the medicine ball's momentum? Okay, so what we'll do is we'll use our formula. Momentum equals mass times velocity. We plug in our information. Okay, 10 kilograms is the mass of the ball, and the velocity is going at is 6 meters per second. We do the multiplication. 10 times 6 is 60. And the units we use are Newton seconds, okay? So the momentum of Drake's medicine ball he threw into air is 60 Newton seconds. Okay, so in order to stop it, the momentum that it's going with, you need 60 newtons applied over a period per second, applied in order to stop it, okay? So momentum, once again, is mass times velocity. P equals mv. So let's go ahead and let's put this in our graphic organizer, okay? P equals mv is the mathematical formula for momentum. Okay, so now that we have that, let's go talk about one other concept before the end. The law of conservation of momentum. Now you might be asking yourself, Mr. Klein, what does momentum have to do with Newton's third law of motion? Well, when action and reaction pairs occur, momentum is transferred from one object to another, okay? Just like the rocket flying, okay, momentum is transferred from one object to another. Or, you know, just shoving someone off of a staircase, okay? As she bounces in, pushes on this other person, okay, she's transferring energy, she's transferring force, she's transferring momentum, okay, from herself to the person sitting on the staircase, okay, and the person falls over. Momentum is transferred over, but it's important to know that How much momentum is there total? Well, according to the law of conservation of momentum, which sounds an awful lot like the law of conservation of mass and the law of conservation of energy, spoiler alert, it's the same thing. Okay, the total amount of momentum in the system stays the same. So if you have a big hit in a college football game, okay, with the running back getting hit by the linebacker, the total amount of momentum of the player running and the player hitting stays the same, even though it's transferred. Okay, before and after the collision, if we measure the momentum of both objects, it's the same amount. Okay, so the momentum is not created or lost, it just transfers from one to the other. Okay, so let's go ahead and let's add this into our graphic organizer and let's wrap up this lesson. That momentum, law of conservation momentum says that momentum stays the same when we have collisions. Okay, and I only wanted just to mention this right here because for our purposes in 6th grade, we're not talking about collisions and impulse or any of that stuff. So if you're watching this and you're taking high school physics or high school physical science, and you're like, well, what about impulses and collision formulas and stuff like that? We're not talking about this in my class. We're just saying that momentum is force, it's the mass and the velocity of the object, and that whenever they do collide, the total amount of momentum does not change. So, Newton's third law, for every action there's an equal but opposite reaction. We know that forces act in pairs. They're the same size, the same amount of force, but they act on different objects. And because they act on different objects, they don't cancel each other out and motion takes place. We can measure how hard it is to stop something moving in these action-reaction pairs through momentum. Okay, it's the measurement of how hard it is for an object to stop. We use the mathematical formula P equals mv. Momentum equals mass times velocity. That tells you the total amount of momentum, and we use Newton times seconds as the units to measure them. And the law of conservation of momentum says that when you have a collision or you have these action-reaction pairs, that the total amount of momentum acting on all these objects is the same when it gets transferred. No momentum is gained or lost. So there you go. That's your lesson, and that's your chapter on Newton's 3 laws of motion. Hope you understood it. Hope you were mildly entertained. And if, as always, you have any questions, please let me know, and thanks for watching.